We start right away with our first session, Deep Learning for Images. And our first speaker is Peng from Helmholtz Munich, and she will be speaking on AI for microscopy analysis and computational pathology.
Okay, thank you, Charlotte, for this nice introduction. So I hope my slides come out. Okay, so I'm Ting Yin, so I'm a group leader at Helmholtz Munich. And my group basically working on AI for computational pathology as well as quantitative microscope images. So we work on all kinds of microscope images, like bright field, fluorescence, like most are 2Ds, but we also work on the 3D light sheet microscope and tomography, electrotomography. And one thing we work particular, which is more linked to clinical setting, is this histopathology slice. So you have already saw Sophie Wagner's talk yesterday, so half of the group working on this direction. So the focus I'm going to talk about is the other half, which is work on the bioimaging side. So we know for microscope images, one thing always troubles us, which is it's too much of noise. So we have like this imaging denoising problem. Well, this is not a problem for computer vision images. So if you have a natural image, usually you can have ground truth with some kind of high-end cameras, and then you can use this ground truth to denoise your bad image into the good image, which is very straightforward. Use a UNet, and it works mostly fine. But for microscope image, the trouble is usually you don't have this clean data because you're already, the hardware setting is already the cutting edge settings. You couldn't use a better camera anymore. And it's already go to like this optical diffusion limit. So you couldn't go further. So you always have a lot of noise. And how to get from this to this? Sounds kind of magic. And that's because there is a family of algorithms called denoising, so noise-to-noise training, which is imaging denoising without clean data. So how it works is if you have like UNet, and now you can use also transformers, you basically, your input is one noise version, and your output is the other noise version. So basically, you need two noise versions of the same thing. And then you train, that's how you train your network. And then during the inference, it automatically gives you a denoised image. That sounds quite magic. But there is a mathematical explanation out of that, because noise, especially random noise, it's very hard to predict. It's non-predictable. So it's not encoded in the UNet or in the network architecture. So the network only encodes the structure information. And then when you pass a noisy image into that network, you will automatically get the denoised image. Then the question is how to find out two noise versions of the same thing. Well, this exists for some image, like this is electrotomography, because it's constructed from tiered series. You have like even tiered series, you have odd tiered series. You basically have the two different noise image of the same thing. But for a lot of image, you don't have this. So you have to like somehow create two noise versions of the same image. Then there is also tricks to do it. One trick, or one recent trick, is called like this zero-shot noise-to-noise for single image denoising. This was published in the CVPR, also from TUM, developed by a group of TUM. What they do is you have these images, and then they basically patch it into this like white and black, two subset of image, and you can see it's like half the resolution of the original image. And that serves you two noise versions of the same image. And indeed, that works. And another group take these ideas and then apply to the bioimages. So that's what they exactly doing. So they basically pad it. And then they also upsample it, so to the original resolution. Those are some kind of detailed tricks, but the essential idea is to create two noise versions of the same image. And then they train a UNet, and then that actually do the denoising purpose. And it works for this super resolution live cell images. You can see the low image and the ground truth, and then after denoising, it seems works pretty good. However, if you take a very close look, you see a bit problem on the background. I don't know how good you can see it, because the background, which is supposed to be 0 or is supposed to be completely dark, but you see some kind of patterns on the background. And this is because this noise, single shot noise denoising algorithm will work perfectly if you noise as like strictly Gaussian white noise. But for microscope settings, this is not the case. So we don't always have Gaussian noise, we have personal noise, and sometimes it's also correlated with foreground. So that's create a correlation of the background, which creates this kind of patterns after denoising. And that's also shows on the original paper of the CVPR paper, and you also see the background on like this medical imaging denoising. So we have to do something. So my student, Thomas, and he invented this. So after doing this, he also shuffled the network. And then he solved this background problem. So the idea he did is, instead of taking this diagonal subsampling, he took random sampling. So he basically took a random sampling of these 4 pixels, and then that break out the correlation or correlation between the background. And after this random sampling, you actually don't have this background problem after in the denoise image anymore. But you have another problem. So you see the foreground looks like this kind of fibers seems to be enlarged, and that's because of it's getting blurred. So you basically have a problem on the foreground. That's why in the last step, what he did is he fed this blurred image in and used the original noise image as the output, train another denoise network. So the in is basically the background is already fine, but the foreground is a bit blurred. And the output or the training target is the noise input, which have all the structure information. And through this way, he can recover the structure back from the noise image. And at the end, you don't have a problem on the background, you don't have a problem on the foreground, and it's all fine, all to go. So indeed, this works. So he simulated noise on the medical images, and because it's a simulated noise, and he can compare that to the ground truth, use the PS, PNSR, or structure similarity, and it works very nicely. And he also tried on the real images, which is the microscope images, which he doesn't have really the real ground truth. But he did have this kind of pseudo ground truth, which is the average of multiple caption of the same samples. So if you average that, noise is gone, and that can serve as a ground truth. And indeed, our method, usually normally achieve the second best, and it's similar to the best algorithm, but our method is much quicker. It's the inference time is 24 seconds, so it's already 15 times quicker than the other method, which is trained in a self-supervised way and need a lot of training. And we don't only the denoising is actually used in the microscope imaging action. So this is our joint publication with Jian, very recent one. With this, Jian have this very cool imaging sensor for the bioluminescence imaging. So basically, you don't need fluorescence, and it have less. They basically have 0 photon toxicity. And then after that, denoising, and you can see in the background, you can see this kind of cell-to-cell communication pathway much better. We also developed research software such as this Basic Pi, which basically do the illumination correction, and that's already used widely in the community with a monthly download close to 2,000. We have this membrane segmentation. So we segment these membranes from quite long electrotomography, and that's already used by CZI to segment over 13,000 tomograms within 3 days. So something you cannot do without a tool, and that is currently under review by Nature Method. We also have this light sheet microscope. So usually for light sheet, image attenuation is one problem. So if you have one illumination camera and one detection camera, and you only got around a quarter of your samples to be okay. But we have a fusion algorithm which fuse 2 volumes, 4 volumes into the same one. So we are fine. We can image the whole volume in a nice way. That's currently in revision by Nature Method. We are not only working on the microscope, we are also doing the fan. The same thing we create for the microscope image, I like this low light enhancement, can works on these movies, so Game of Thrones. So usually like the people are complaining it's too dark, and then we can like make it brighter and you see all the details. Okay, so this is the end of my talk, and I'm very happy to take any questions.
Thank you. It's a bit intimidating to walk up to this. Thank you for this talk. Very interesting. I'm sure we have questions. Go ahead.
Hello, I'm Wahid from Daisy. Thank you so much for a very nice talk. I have 2 questions. It seems that you are using standard unit model with standard loss function like MSE. And we know that in MSE we have, after reconstructing the image, we have contrast shift. So how you deal? Your result shows that the contrast is different with your input image also.
Yeah, that's a very, very good question. That's actually also bothering us. We currently don't have a solution, but we also realize the problem. So because for some of the images, you don't want to change the dynamic range or your original intensity. You want to put it in the same range as the denoise, like before the denoising. So we also think about like maybe we can use other loss function, like something else, rather than MSE to enforce that. It's still in progress. Yeah, if you have ideas, then I'm happy
maybe you
to
should come to
discuss.
my poster session today.
Yeah, sure.
And
thank you.
And also the second question is that the unit model is a generative model, and how you guarantee that the model doesn't generate any new feature?
Mm-hmm. Yeah, that's also a very good question. So there is generally 2 ways to do it. And there is this recurrent Lucy network, so something like mimic like the classic deconvolution network. And so it's forbidden to generate something like super, it's basically it stops it from hallucinate something. Or you can use a unit with like a small shallow unit, and so it cannot hallucinate a lot of things. So there is other tricks to do it. Or alternatively, you have foundation model, and then you see everything and you create everything.
Maybe I have one more question. How long does it take for training your model, and how much data do you need for it?
For this, the work I show, like this noise to details or Thomas Mikai paper, and that's zero shot. That's one shot. I mean, that's it, 0 shot and 1 shot. So you just need a single image, and that's it.
Okay. Thank you so much.
Thank you. I also have a question that sort of ties into this very well. You showed sort of the sequence of different steps that you train models to do. Do you need to train them individually and sort of separate, or can you chain them actually and train them jointly in basically one large pipeline?
Mm-hmm. That's a very good question. So currently we train in a sequential way. So we train the first one, and then we use the input for the second one. We haven't think about train jointly end-to-end fashion. That's something we can explore in the future.
Yeah, okay. Do we have further questions? Okay, then thank you again.